We're going to learn about probability. Probability. I think I'm recording now. Am I recording now? Looks like I'm going. Probability. I have trouble with spelling. Probability. This is 8-6. Okay. The probability of an event is. Well, we'll talk about we've talked already a little bit informally about probability, but a probability outcome has two parts to it. Okay, it has a sample space, right? It has a sample space. A sample space which is all events that all of the possible outcomes of an experiment. All of the possible outcomes of an experiment. Okay? So if you were to roll a dice, what's your samples? Roll one die. What's your sample space?
1 to 6.
Yeah, and you list it as kind of a set, like 1. You can get a 1, you can get a 2, you can get a 3, you can get a 4, you can get a 5, or you can get a 6. Yes? Yes? And an event, and then you have an event. An event is a collection of sorry, it's a sub collection of the sample space. It's a sub collection, is that one word? A sub collection of the sample space. Okay? So for instance, you could say, if I roll a dice, what's one sub collection of rolling a dice? 1 and 2, right? Numbers less than 3. I could have a sub collection where I could say odd numbers, right? 1, 3, 5. I could say even numbers. I could say just the number 6. I could say the number 7. What would happen if I said the number 7? You'd have a 0 probability, right? And so when you're finding a probability, okay, so let's do, like, for example, I can't talk. Can you see that blue? No, that's not very good blue. Let's get a dark blue. Dark blue. Ooh, that's a good blue. Okay. Okay, so 2 coin tosses. 2 coin tosses. What's the sample space? What could happen if you can get, so all possible things that could happen, I could get a heads, and I could get a heads and a tails. What else could I get? I could get a heads and a heads. What else could I get? I could get a tails and a tails. What else could I get? I could get a tails and a heads, right? So you got to be careful because there's 2 ways that you could get 1 head and 1 tail, right? So what's the probability if you toss a coin twice that you'd get 1 head and 1 tail? 1/2, right? 2 out of 4, right? What's the probability if I toss a dice that I get a 3 or a 6?
Oh,
right?
no.
If I toss a dice, what's the probability that I get 2 or 6? 1/3, right? 2 and 2. There's 2 possible things. So that leads to the definition of probability. Okay. So probability of an event. Okay, is equal to the number of ways that the event could happen, okay, over the number of elements in the sample space. Hi.
Hi.
Emerson Herman, you have to go when possible. Okay. Can you into? No, you can't. Sorry. Okay. So this is the probability of an event. Probability is equal to, this is the number of ways an event can occur. And so this means and this is the number in the sample space. So if I say what's the probability of getting a heads or a tails is equal to, how many ways are there to get a heads or a tails? Heads or on two tosses. A heads and a heads and a tails. A heads and a tails on two tosses. Right? It's 2 out of 4, which is 1 half, which is 50%. 50%. Yes?
Yes.
Questions?
Why?
All right. Why? Because also probability always has to be a number. Probability is always less than or equal to 1 and greater than or equal to 0, right? So it always has to be a number. You can have a probability of 1, right? How could I have a probability of 1? What's the probability? Let me tell me how I can get a probability. What? What's the probability on one coin toss that I get a heads or a tails? What's the probability if I pick a card from a deck that I'm gonna get an ace through a 2, right? An ace through a 2, right? Right? Or a 1 through a king, an ace through a king, yeah, or something like that. Okay. All right. So now what? So if I roll 2 dice, am I getting ahead of myself? What's well, let's not go there yet. Yeah. Well. Okay, let's talk about cards. Do you know about cards? So roll cards. There's 52 cards in a deck. 52 cards in a deck. Okay. Okay. Most decks have 50. Do you play cards?
What about
Like jokers?
Joker?
Do you guys have 52 cards in a deck?
Yeah.
Okay. Because if you're not playing with a full deck, which is the case for many of you. Okay, no, I'm just kidding. I shouldn't be not nice. Okay, so 52 cards in a deck. What's the probability of getting a heart? What's the probability of getting a heart? Heart.
1 in 4.
1 in 4? No, yeah, you're right. There's how many hearts are there in the deck? 13 out of 52, right? What's the probability of getting a 10? Probably getting a 10.
4 in 52.
Probably a 10, there's 4 out of 52. Okay? What's the probability of getting a heart or a 10? Ooh. What do I do with those two? Is it 17 out of 52?
16.
Why is it 16 out of 52?
There's already there's a 10 of hearts.
Ah, very good, and you're counting it twice, right?
Yeah.
So that's called. So that's not mutually exclusive. I'll talk about that in a second. So another way to write this is the probability of heart union. No, it doesn't have a tail on it. Union, it's just like a, have you seen this symbol before? U, like a straight up U. Our union 10 is equal to 17 out of 52. You said I have to subtract 1 out of 52, right? Which is equal to 16 out of 52, which reduces to something, right? 13 out of 26. That's, I think, as far as I, is that? That's, what did I just do? 8 out of 20. 8 out of 26? Which is 4 out of 13. Is that right?
Yes.
4 out of 13. Okay? So this is the same thing. 4 out of 13. All right? So mutually exclusive, okay? Mutually exclusive, okay? Exclusive means, okay, can't happen at the same time, okay? Can't occur at the same time. At the same time, okay? So for instance, you can't do the if you flip one coin, the probability of a heads and a tails is what? 0, okay? Equals 0. So for mutually exclusive events, the probability of U, or the probability of A or B, is equal to the probability of A plus the probability of B. Okay? So for instance, in Mr. Reader's math class, so I have some seniors, right? I have some seniors. Do I have some juniors? Do I have some sophomores? Do I have any freshmen? I had a freshman. But, okay, the probability that you are a freshman, or the probability that you are a junior, or probability that you're a sophomore, or the probability that you're a junior, or the probability that you're a senior, they're all mutually exclusive, right? Because you can't be a sophomore and a junior at the same time, okay? So some examples of mutually exclusive: probability of a sophomore or a junior, okay? Or a junior. For mutually exclusive events, the probability of both things, HNT, is what you write like this, with a up HNT, if you throw one coin, is equal to 0. The probability of sophomore or junior, okay, is equal to the probability of sophomore plus the probability of junior, right? Yes, probability of sophomore or the probability of the junior. You get that? Okay. What's another mutually exclusive event? Rolling a dice and getting a 3 or a and a 5. How about rolling a dice and getting a 3 or an odd number? Are those mutually exclusive? No. Okay. If they're not mutually exclusive, okay. So if they're not mutually exclusive, not mutually exclusive events, okay? Another word for mutually exclusive is called disjoint. I don't know if they use that in the book, but disjoint means there's nothing in common, okay? Mutually exclusive, if you were to do a Venn diagram, here's A and here's B, okay? Not mutually exclusive, not mutually exclusive, you have a Venn diagram that looks like this, okay? You have a Venn diagram that looks like this. Here's A, here's B. What does this represent?
C.
It's C, but it's A and B. You understand that? Okay? So in probability, the probability of A, if it's not mutually exclusive, the probability of A or B is equal to this is kind of what you did with the hearts, not heads and tails. What you did with the the hearts or the 10, right? Hearts are 10. Probability of A plus the probability of B minus what? The probability of A and B. Okay? So for instance, if I were trying to find the probability of, so say I have 10 people, 10 people that have 10 people who are girls. Okay? So A is girls. A equals girls. A is the event girls. B is the event brown eyes. Brown eyes. Okay? Brown eyes. Okay? And say I have 20 people with brown eyes in my class. Okay? Say I have 7 girls with brown eyes. Girls with brown eyes. Okay? So, how could I figure out the probability that I am a girl or I have brown eyes? Girl or brown eyes? Whoops, I shouldn't have a tail on there. What's the probability that I'm a girl or I have brown eyes? What's the probability that I'm a girl? In my class, say. Let's just pretend that. Probably, so I have 10. What's the probability that 10 out of, let's say that, this is my whole class, right? So how many people are there in the class? There's, that's tricky, right? You don't know. 10 out of, we'll figure that out in a minute, okay? 10 out of something, right? What's the probability that I have brown eyes? Brown eyes. 20 out of something. What's the probability that I have both? What? 7, right? 7, right? But how many people are in this class altogether? Okay. So there's 10 here, but 7 of them are here, right? So how many are actually out here? What is 3 here? How many are here? 7. How many are out here? 13. Do you understand that? Yes? No? So altogether, how many people are in my class?
23.
23 people in my class. So this, I'm getting kind of making it kind of tough, you know. But there's got to be 23 altogether. You understand why there's 23? Right? Because, right, if there's 10 people that have brown eyes, there's 10 girls in the class, there's 20 people with brown eyes. So what does this represent? What's that 13 represent?
People with brown eyes that aren't girls.
People with brown eyes that are not girls, right? People with brown eyes that are not girls. Very good. Yeah, Ben gets it. All right. So, what's the probability that I'm a girl or I have brown eyes? 10 plus 20. Wait a minute.
Yeah.
That doesn't make sense.
If you do that, you're assuming that everyone in the class is either a girl or has brown eyes.
Oh, let's put some people out here. Here we go. Oh, I did a really bad problem.
I think we should.
That's what happens when I try to make up stuff as I go. Okay, let's do another one. Now. Okay, I'm gonna stop the recording now. Okay. What?
Also, should that say exclusive, not because you just said it's not.
Oh, I'm sorry. Mutually, why didn't you tell me that? Mutually exclusive. I'm sorry. Okay. So yeah, it should look like that. Yes, sir.
But shouldn't 4 be
It's not mutually exclusive because you could be a girl and you could have brown eyes, right?
Right.
But you could, so like you can't. So in other words, there's girls who don't have brown eyes, right? Well, there's girls, right? And then there's girls without brown eyes, right?
Am I just trying to
I should have used a different example. Okay, here, let's do it. Let's do
An
it.
example from the book.
But no, I want to do my own example.
Won't be here all day.
But
Yeah.
what I'm asking more specifically is, do we use either or and for, is either or and like assigned to either mutually exclusive or not mutually exclusive? Like is one go with the other? Or-
No, no.
Okay.
Yeah, and could be both things at the same time, right? So, and if two events are mutually exclusive, then and is going to be 0, right? And is going to be 0. So I have I love God. No, you can't do that either. Okay. I'm in 9th grade or I'm in 10th grade, right? Those are mutually, so the probability of being in 9th grade and 10th grade is 0, right? But I'm in 10th grade. I'm in 10th grade, or I take pre-calculus, right? So I'm in 10th grade. That would be a better example, right? I'm in 10th grade, or I take pre-calculus, or people do both, right? So those are not mutually exclusive.
Depends on the context.
Depends on the context. Okay. All right. Let's do one. Let's do one. In a deck of cards. What's the probability of a 4 that you're a 4 or a 6? What's the probability that you're 4 or 6? Are these mutually exclusive?
Yes.
Mutually exclusive.
Yes.
Yes. Okay. Mutually exclusive. So you have a probability of 4, right? Or the probability, or plus the probability of 6. What's the probability of a 4? How many 4s are there?
1 in 13.
4, yeah, 4 out of 52, which is 1 out of 13, plus, how many 6s are there? 4 out of 52, okay? Which is 8 out of 52, which is, what does that reduce to? 2 out of 13? 2 out of 13. What's the probability that you're a queen, okay? Queen or red? These are probably better examples. Or a red card, okay? Queen or red, try that again. Queen or red card. What's the probability that you're a queen? Probably a queen. Plus the probability of red, right? Minus, how many red queens are there? 2 that are queens and red, right? Right? So probability of queen is how many out of 52? 4 out of 52. How many red cards are there? Red cards. There's 26 out of 52, right? How many are queens and red cards? 2 out of 52. Does that make more sense? That's a much better example, right? Better example, okay? So that's 30 minus 2. So probably, so that's 30 minus 2, which is 28 out of 52, which is 14, which is 7 out of 13, right? Yes? And so this is not mutually exclusive. Let me write not mutually exclusive. This is yes, mutually exclusive. Whoops. Not mutually exclusive. This is mutually exclusive. Mutually exclusive. That's a better example. Is that a good example? Thank you. All right. All right. We're going to pause here. Are we going to pause?
I think we're just going to dismiss the class for today.
Did you hear about that bear that walked into the bar? No, I heard, yeah, but the bartender said, "What do you have?" And the bear just sat there. And he said, why the big pause? Okay. You need to stand up and sit down for a minute?
I
No?
think we all need to take a field trip to
Yeah, we need to go gambling. We're gonna do that tomorrow. Tomorrow, we're gonna do, yes, Daniel,
So how did you find the probability of it being
here we go. Okay, independent events. Independent, so a lot of people think that independent means the same thing as mutually exclusive. It doesn't, okay? Independent events means, okay, so what happens in the, what happens in the second event? What happens, oh, come on. What happens in the first, come on, let's try again. What happens, this is why I'm getting that thing, right, Melissa?
I just go with it if this
What happens in what happens in the first event? The first event does not affect. Event does not affect. Does not affect. Affect. Okay. The second. Okay. So, for example, yes,
so would that be like taking a marble out of a bag, putting it back in?
and putting it back, exactly. Okay. So, replacing cards, replacement must occur. Okay. Replacement must occur. Okay. So, yeah. So if you're playing cards, right? If I pull out a 3, what's the probability that my second card is gonna be a 3? Are those two probabilities the same? If I pull out a 3 on the first trial, if I pull out 2 cards, what's my probability that I pull out a 3 on my first trial? 1 out of 13 or 4 out of 52. Okay. If I get a 3 on my first card, right? What's my probability that my second card, and I don't put it back in the deck? What's the probability? 3 out of 51. What's the probability that? So if I don't put it back, right? If I pull out if I don't pull out a 3 on the first card, what's the probability that my second card will be a 3? 4 out of 51, right? So the denominator changes as well. Those are not independent. But if I put that card back in each time, then they are independent. Same thing with marbles, taking marbles out of a thing. That's when you make a tree diagram or something like that. Okay? So you do that a lot, and we do that a lot in statistics. Okay? So for independent events, the probability of A and B, okay, A and B, okay, is equal to the probability of A times the probability of B, okay? So what's the probability? So for instance, okay, you could use this symbol as well, an upside down. So if a family, so what's the probability if you're having kids, okay? What's the probability of having a boy, roughly? Say the probability of having a boy is 1/2, okay? What's the probability of having 3 boys in a row? 3 boys in a row. What do I do with those 3 that's right, Jessica. It's 1/2 times 1/2. Probability doesn't change, right? So a lot of people say, okay, these are independent events. So my mom, she had 3 boys, right? She had 2 boys, and then my my older brothers, they grew up really fast, and then she goes, oh, they were kind of almost in college. Like there's a big space between me and the other brother. And then they had my third brother by mistake. We always tell them that. And then I was a mistake since I was the youngest. They made me to keep my other brother company, you see. So, but we were all 4 boys. What's the probability of having 4 boys in a row? 1/16. 1/2 times 1/2. What's the probability if you had? So if you have three boys in a row, what's the probability that your 4th child will also be a boy?
1/2.
It's 1/2.
That's
It
the
doesn't
way to
change
think.
it. It doesn't change, right? So the probability, it's always going to be the same. So what's really weird is then my brother, who for a long time was my oldest brother, is the only one in my family who had kids for a while. He had 4 boys as well. So in my mom, she had like 4 boys, and then she had 4 grandsons. What's the probability of that, right? 1/2 to the 8th power, right? Finally, I had 2 girls finally, and my other brother had a girl. So, any case, but so that's the way. Independent, you just multiply together the probabilities, but that's not always always the case. So that's how independent events work. And then dependent events, we'll talk more about that later on. But a couple other things, which very early on, am I recording? I am recording. That Ben was getting to is the complement of an event. Complement, okay? Complement of an event. And complement, we're going to do the birthday game in a minute. Complement of an event, okay? So the complement of an event, written if P of A is some event, okay? It's some event, okay? Some events like it's raining out, the probability that it's raining, okay? The probability of, in this book they use the symbol A prime, okay? In our stats book they put a little C up here, is equal to 1 minus the probability of A, okay? So if the probability that it's going to rain today, or snow today or something, rain today is 30%, right? What's the probability that it's not raining? Not raining. Not gonna rain. Gonna rain. What's the probability that's not gonna rain?
70.
1 minus, we write the percent as that, which is 0.7, right? Which is 70%. So that's a lot of times when you're figuring out probabilities, it's way easier to figure out the complement and to find the answer. So that's how the birthday problem works. You ready to see how many of you have the same birthdays? Okay, here we go. Okay, we're going to stop. We're going to pause for station ID. Okay, so the probability that of same birthday, B-day, okay? I don't have this question on a test, but it's a good one, okay? Is if there's 28 kids, 28 students, is you do it by going 1 minus the probability that people don't have the same birthday, okay? So say I line up everybody in the class, okay? I were to line up everybody in the class. How many choices do I have for my first spot? If there's 28, well, we actually did 29 because I counted 2, right? So how many choices do I have for there's 29 people in the class. How many choices do I have for birthdays with 29 people for spot 1? If I want no one to have the same birthday. No, how many days in a year?
6.
I have 365, right? Yes, I have 365 choices. If I want no one to have the next birthday, how many choices do I have for the next birthday? 64, right? I can't choose. So basically what this had, I go 365 choices for the first spot, 364 for the second spot, dot, 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 dot. I don't go all the way through all the days of the year. Yes?
How would that work with leap years?
Don't get me confused, okay? It's not- Come on. Ethan, we'll worry about that in a minute, okay? Yeah, we'll worry. But 365 times 364, and down until I got to, how many spots would I have altogether? 29 spots, okay? So the way you can do this is 1 minus 29. This is a permutation, not a combination. 1 minus 20, excuse me, wrong. 1 minus 365, permutation. 1 minus 365, permutation 29, right? That's how many different combinations there are. But if anyone could have any birthday they wanted, right, what goes in the denominator? If it could be any birthday. What? 365 to the what power? To the 29th power. Do you understand that? Right? Because if this spot could have any birthday, that spot could have any birthday, that it could be any day of the year, right? So it's a probability of no one having the same birthday out of 29. This is all the ways you could have. No one could have the same birthday out of. You could have any birthday you want, right? Okay, so there's everyone get 365 choices for Jessica, 350, 65. So if I do that on my calculator, watch. Okay, let's just do it on your calculator. Okay, see what happens, because this is a fun problem. Where's the mouse? Your mouse. Oh, there he is. Whoa. So there we go. And then you'll have time to work after this, because this is the fun problem. So I'm going to do 3. I'm not going to subtract the 1 minus yet. I'm going to go 365 math, PRB, 29, which if I try to do that, it'll probably give me an overload. So I'm not going to do that yet. So what I'm going to do is,
It says 9, that's why
whoops, 29.
It will give you an overload.
Well, in any case, I'm going to go over here, over here, over here, and I'm going to divide that by, and I'm going to put in parentheses, 365 raised to the 29th power. Okay?
No, that's divided.
Divided by. Sorry. Raised to.
It's the little part.
I know that. Come on. The 29th power. And I'm going to delete that. I'm going to put a thingy there. And then this represents, right, how many ways are there for people to not have the same birthday. So that's the probability that no one in a group of 29 people would have different birthdays. Everyone would have different birthdays. So if I subtract that from 1, okay, I'm subtracting 1 from, it's going to be with 68%. So if I did this as a class, if you had a class of 29 people, 68% of the time, at least 2 people, that doesn't mean that 3 people couldn't have the same, at least 2 will have the same birthdays. Isn't that interesting? Okay? And that's my favorite problem. So anyway, that's how you do that one. And just to show you on Schoology, the other thing, the problems that you have for homework are pretty straightforward for the most part. You'll ask me some questions, but I was trying to do last night, I was trying to do card problems and full houses and all that kind of stuff. And you can do all that stuff by multiplying probabilities, but this shows you like you're not gonna have to do like really complicated card problems for on a test or anything, but they're kind of fun to. Whoops, that's not what we're doing. What? We're doing that tomorrow. That's gonna be fun. But 5-card poker hand probabilities. I found this. This is on my Schoology. But like the way they figure out these probabilities is it gets pretty complicated with the combinations and stuff like that. But what they do, so this says like a single pair. 13 choose 1, which means 13 combination 1. That's the number of different card denominations you could have, right? So you're choosing one card, so this is for 2 of a kind. Choosing one card denomination, 4 choose 2. What does 4 choose 2 mean? So this one says choose one card, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up through ace. This says choose the number of ways to arrange 2 of the 4 of that particular card. So this would be the number of ways to arrange, like say your card that you chose was a jack. So this is the way to arrange 2 jacks out of 4. 12 choose 3. Now you have 12 suits remaining, and you want to pick 3. You want to pick 3 cards. 3 cards out of those 12. That's the number of ways to arrange those 3 cards. 4 choose 1. That's, what is 4 choose 1? Oh, you want, I'm not sure. Raise to the 3rd power. It gets really complicated when you're doing card hands and stuff like that. And then you always put that all over 52 choose 5, because this is the number of possible card hands that you could have. 52 combination 5, that's the number of ways to arrange a number of arrangements of a 5-card hand with 52 card deck. That's what that one is. But you should know 52 choose 5, but you could just look at those and see if you can figure them out, but they can get really confusing. So anyway, that's it. Your homework is right there. You can start on those and ask me questions, and you have a good half hour, right? Half hour? 20 minutes? Did I talk too much? I talk too much, but it's okay. Yes, you may go to that.